Hello, Assalamu alaikum everyone. I am Maisha Jarin with you all, and today I am delighted to present our research on pattern recognition of partial discharge image based on 1D CNN. In this presentation, we will explore the challenges in power system equipment maintenance, the importance of pattern recognition in insulation evolution, and how our innovative approach addresses this issue. So let's move on. Our research was conducted by a team of dedicated experts from Department of Electrical Engineering at Shanghai Jiao Tong University, China. Big data platforms and centers which store unstructured data like images are everywhere. The partial discharge pattern recognition method has been extensively studied for structured data, but traditionally methods can't be applied to unstructured data. To this end, a one-dimensional CNN-based time-domain waveform pattern recognition was proposed. One-dimension waveform characteristics are obtained using image processing. Deep learning build the pattern recognition network simply. Image data sets of five partial discharge defects are created and compared using on-site detection and simulation experiment. Testing shows that proposed method can recognize patterns for data mining and utilization. It is more accurate than a two-dimensional CNN at the same complexity. The method also extrapolates features without manual extraction, reducing experimental complexity and robustness. The main power system equipment, gas insulated switcher GIS, affects power grid stability. Most equipped fails due to insulation degradation. Through partial discharge detection, classification, and location, insulation performance is assessed. The traditional steps include building partial discharge pattern, extracting features from signal, and selecting pattern recognition algorithm. Recent domestic and international discharge pattern recognition research focuses on feature extraction from detection method and algorithm construction. MFDFA based feature extraction was suggested to improve partial discharge recognition. After extracting fractal parameters from three-dimensional energy spectrum, the Hilbert-Huang transform HHT enhanced fractal features and classified partial discharge defect with neural network. Deep convolutional neural network recognition recognized PRPS pattern. These studies classify partial discharge defect using structured two-dimensional or three-dimensional spectra. Due to high frequency and ultrasonic detection, partial discharge on site detection has collected substantial data. Portable data detectors use unstructured datasheets like images for speed and convenience. High sampling rates are typical for oscilloscopes and positioning instruments. Directly exporting partial discharge waveform binary files takes time and storage. Keeping multi-cycle wave files reduce data. Big data platforms store most time domain waveform data as unstructured image. No research has examined partial discharge time domain waveform image. Partial discharge image cannot use structure partial discharge pattern. Big data platform based on detection instead of machine learning classification. Deep learning based time domain waveform recognition is suggested. Time domain waveform image was experimental simulation and on-site detection are used to build a one-dimensional CNN model for supervised training. The model recognizes patterns and extrapolates features from partial discharge image without manual extraction. This method simplifies artificial features extraction and preserves manual data selection. Inputting the original image and using deep learning model improves detection and big data platform data utilization. This selection outlines the process of data collection and preprocessing. The researchers used a high-frequency data detection system and an oscilloscope to capture time-domain waveform image. This image represent voltage signals with samples of 4 GHz. To manage the large amount of data, image segmentation is applied, which results in two-dimensional array. The images are then converted grayscale using a method involves three channels R, G, and B. The grayscale images are globally binarized based on threshold 60 to highlight specific features. The study includes five detect types: floating discharge, partial discharge, corner discharge, insulation discharge, and interface. Time domain wave images are composed of 5 consecutive cycles of partial discharge pulse rate, each lasts for 100 ms. These images contain two channels, one close to device under detection and one farther away. The paper introduces a 1D CNN network for pattern recognition. Unlike traditional 2D CNNs, the 1D CNN uses 1D array to convolutional kernels and feature maps, making it suitable for time domain and waveform data. 1D CNN's forward propagation is calculated using a defined equation incorporating activities, function, bias, values, and weights. To adapt the 1D characteristics of time domain waveform, each column of 2D matrix is summarized, obtained 1D array representing the amplitude of partial discharge voltage. Linear normalization is then applied. The pattern recognition procedure is detailed and it consists of the following steps. Number 1. Processing of time domain wave images and linear normalization of resulting 1D array as input data. Number 2. Training the constructed 1D CNN model on a training set. Number 3. Updating of model parameters using stochastic gradient descent and cross entropy cost function minimization. So number 4, supervised fine-tuning through the backpropagation algorithm and model optimization. Number 5, image segmentation of original test image resulting in 4 sub-images. The sub-images are prepared and normalized and the softmax clarifier is applied to determine the probability of 5 defect type. A voting method is employed to reach a classification decision. In this section, we present the outcomes of our research focusing on pattern recognition using a one-dimensional convolutional neural network, 1D CNN driven by deep learning. Our data was categorized into 5 distinct groups: floating discharge, partial discharge, corner discharge, insulation discharge, and interference. To gauge the model's practicality in engineering application, we analyzed a total of 1,800 cases. To enhance the model's robustness and generalize, we employed a five-fold cross-validation approach on 1,440 images, reserving remaining 350 for a test set. This methodology provides valuable insights into model's performance. For 4 of defect types, a majority of 70% samples were derived from one-side detection, while remaining 30% originated for simulation experiments. It's worth nothing that all samples of the interface type were exclusively obtained through on-site detection. Furthermore, in case of same defect, half of the samples were collected from same device at various discharge time within the sample detection position, while the half were sourced from different devices. The 1D CNN model underwent an extensive training process consist of 24,000 iterations with a learning rate of 0.005 and employed mini batch training. The results were thoughtfully summarized in Table 1, providing a clear depiction of recognition accuracy through a confusion matrix. This section encapsulates our empirical findings, highlights the model's capability to effectively classify different types of partial discharge, and its suitability for real world engineering applications. To access the performance of our pattern recognition model, we compared it to other models, specifically support vector machine (SVM) with a radical basis function kernel and backpropagation neural network. SVM employed a gamma parameter of 0.01 and penalty factor of 12,000, while BPNN underwent 4,000 iterations with a learning rate of 0.002. The comparison results are outlined in Table 2, demonstrating that the proposed 1CDNN model significantly outperformed other methods. We also considered time complexity of our CNN model, which determines training and testing time. A comparison of 1D CNN and 2D CNN model under the same time complexity was conducted. Notably, the 1D CNN outperformed the 2D CNN, particularly expressing the 1D information of voltage pulse. The efficiency makes it a favorable choice for time-domain waveform characteristics analysis. Overall, our experimental results validate the effectiveness of 1D CNN model with an average recognition accuracy of 88.9%, and it showcases its potential in pattern recognition for partial discharge image data. These two sections encapsulate our research findings and their implications, emphasizing the strength of the 1D CNN model in analyzing time domain waveform data efficiency and effectively. Classifying a partial discharge type of unstructured time domain waveform image was proposed in this paper. Big data technology accumulates unstructured data like partial discharge image on site. The proposed algorithm directly processes unstructured data and simplifies pattern recognition features extraction. The accuracy is higher than SVM and BPNN. It reduces experimental complexity and is robust. This method works for other unstructured big data platform data. This is crucial data mining and data utilization efficiency. So, thank you so much everyone for staying with me. Allah Hafiz.